In this video, we will be looking at section 2.2, which covers graphs of linear functions. We do need a definition because we'll be using it throughout this section, and we've already talked about it a little bit. We're going to talk about intercepts. An intercept is a point where a graph crosses an axis. An x-intercept is where the graph crosses the x-axis, and a y-intercept is where the graph crosses the y-axis. In the last section, when we were talking about y equals mx plus b, b gave us our y-intercept, and that's because that value b is the same as y when x equals 0. We'll get some time to look at these intercepts as we move through the section. We're going to start by graphing some basic linear functions, and we're going to start by doing this the way that a lot of high school students and even college students and beyond really like to graph linear functions. We are going to use the fact when we're dealing with y equals mx plus b, the y-intercept is located at the ordered pair 0, b, and from there we will use the fact that m can be thought of as rise over run. So let's see what we can do with this. First up, we have f of x equals 2x minus 3. So that means our b value is -3. So our y-intercept is at 0, -3. 0, -3 is located right here. So on our y-axis, we plot our b value. From there, we're going to use our slope as rise over run. Since that 2 isn't written as a fraction, I'm going to write it as 2 over 1. That way I can see that I can rise 2 and go over 1. So up 2 to the right 1, up 2 to the right 1, up 2 to the right 1. And that's given me a really good look at what my line's going to be. Next up, we're looking at g of x equals -3/4 x plus 1. So I'm going to start at the positive 1 on my y-axis. Now I need to decide whether my negative for my -3/4 is in the numerator or the denominator. I have to pick one. I will typically think of it as being in my numerator, just so I'm always thinking of it the same way. So to use a slope of -3/4, I can go down 3 to the right 4. Now it would be equally as correct if you thought of -3/4 as 3 over a -4. So from a point that we know is on the line, we could go up 3 to the right 4. That's just as correct. It gives us another point to work with. Whoops, and I put it too high. Up 3 to the left 4. There we go. You'll see that all 3 of these lie on the same line. For h of x, we're looking at -1 minus 1/2 x. This one's trying to trick you because it's written kind of weird. We like our slope and our variable to come first. So this is a -1/2 x minus 1. That way our slope is first. Our slope is -1/2. Our y-intercept is at 0, -1. So I'm going to start by putting a point there. I think of -1/2 as -1 over 2. So I can go down 1 over 2, down 1 over 2. And that's what we're looking at. This tends to be a favorite way to graph because looking at the equation, there's not a whole lot of trickery with it. You just have to follow the steps. But it's not the only way we can graph. We can also graph linear functions using transformations. So we were talking about transformations in section 1.5 with our reflections, our stretches, our compressions, our shifts. So let's try graphing that way. since we're dealing with linear functions, our parent function from our toolkit functions that we're going to be using is y equals x. That's going to be our base function that we start with. That function I'll graph on both of our graphs, and then we can transform it from there. All right. So let's start with f of x equals negative x plus 3. If I were to graph y equals negative x, then I'm a step in the right direction. This is a reflection. It could either be thought of as a vertical reflection or a horizontal reflection. We can't tell if the negative is quote-unquote outside of the whole function or quote-unquote in front of the x. Either way, it looks the same. So if we do a reflection, that's the graph we're looking at. But that's just the reflection. From there, we need to add 3. So if I graph y equals negative x plus 3, that's adding 3 at the very end of our function. So that moves it up 3. This would be way easier if I had a steady hand, but hopefully you get the idea that I took the orange line and moved everything up 3 units. This purple graph is the one we want because we were looking to graph f of x equals negative x plus 3, and that's what the purple graph is. Next up, we're looking at g of x equals 1/3 x plus 2. So what we have is a 1/3 out front of our function x, so that we can think of this as a vertical compression by a factor of 1/3. So what we're doing is we are taking each of our y values and multiplying them by 1/3. So if I'm graphing y equals 1/3 x, then if I multiply each of my y values by 1/3, we get 1/3, 2/3, 1. 1 1/3, 1 2/3, and then we get the negative values of those. So we're kind of looking at this squished little thing. Finally, we need to add the plus 2 at the end. And we get y equals 1/3 x plus 2. And just like on the last one, that plus 2 is going to be our vertical shift. Since it's plus, we are going to move up. So we will move up 2 units. So everything just moved up 2. So again, the purple graph is the one we want. I just wanted to show my steps of how I got there. You don't have to graph this way, but it is one way to think about it. We are going to look at a third way to graph, and this one's going to be by using intercepts. So again, intercepts are where we cross axes. An x-intercept is where we cross the x-axis. A y-intercept is where we cross the y-axis. If I'm trying to find my x-intercept, then I need to let y equal 0. Because if I'm crossing the x-axis, then my y value is 0. So if I plug in a y value of 0, remember that f of x is just a fancy way of saying y. So I'm going to plug in 0 over here. That's equal to 2x minus 4. I can add the 4 over, divide by 2, x equals 2. So we know x equals 2, y equals 0 is a point on this line. To find the y-intercept, we know we're going to be on the y-axis, and every point on the y-axis has an x value of 0. So if I plug in x equals 0, then f of 0 is equal to 2 times 0 minus 4, which is 0 minus 4, which is negative 4. So we know when x equals 0, y equals negative 4, which is right here. 2 points determine a line, meaning that given these 2 points, I can just connect the dots, and that'll give me my graph. You can check your work with these, which is really nice because we already know how to graph other ways. If you want to plot this graph using the y-intercept and then using the slope from there, that's a good way to check your work. Next up, we're looking at g of x. G of x is equal to 3 minus 2/3 x. Let's start with our x-intercept. For our x-intercept, we let y be 0. So that'll give us 0 is equal to 3 minus 2/3 x. I'm going to add my 2/3 x to the other side. 2/3 x is equal to 3. I can multiply both sides by 3. So 2x is equal to 9. Dividing by 2, I get x is equal to 9 halves. So 9 halves, comma 0, comma 0. I was looking at my 2x from above. So x is 9 halves, my y is 0. That's my x-intercept. For my y-intercept, I let x be equal to 0, and g of 0 is equal to 3 minus 2/3 times 0, which is 3 minus 0, or just 3. So when x equals 0, y equals 3. 9 halves, comma 0. I have to remember that 9 halves, if I divide that out, is 3.5, is 4.5. Geez. So my x-intercept is at 4.5 on the x-axis. My y-intercept is at 0, comma 3, which is up here. I play connect the dots. And that's the graph I'm looking at. There are some special horizontal and vertical lines that feel different to graph. And there's a way to help you remember this. If we're graphing horizontal and vertical lines, it may be helpful to remember the mnemonic VUX POI. What this stands for is vertical lines have a slope that is undefined, and their equations are in the form x equals some number. So for example, x equals 2, x equals -5, x equals 6,000. If x equals a single number, then you have a vertical line, and that slope is undefined. HOI stands for horizontal lines, have a slope of 0, and their equations are in the form y equals a constant. So y equals 1, y equals -3. You have to keep in mind, though, that we are working in function notation, so it might not look quite this clear all the time. So horizontal lines have equations of the form f of x equals b, so they're just replacing our y with f of x. Vertical lines have the equation of the form x equals a. So if you just see x equals a number and you're graphing it, it is a vertical line. So if you come up with an equation that just looks kind of weird, try thinking VUX HOI and see if that'll help you graph what you're working on. So we want to graph the following equations. X equals 3 and f of x equals -2. If I think VUX HOI, since this is x equals, I know I'm in the VUX case. Vertical lines have an undefined slope. Their equations are x equals a number. I have x equals a number, so this is a vertical line. X equals 3 right here, and I'm looking for the vertical line through there. If I'm looking at f of x equals -2, I have to remember that f of x really just means y. And if I'm looking at y equals -2, then that reminds me that I'm looking at HOI, a horizontal line. Y equals -2 right here, and I'm looking at the horizontal line through there. Now, if this Vux-Hoy thing works for you, great, wonderful, use it, I'm happy for you. But it is not always the clearest why it works for people. So let me explain that for a minute. We know that if I give you 2 points, then there's only one line that goes through those 2 points. So if we can find 2 points on this line, hopefully I can help reassure you that we have drawn the correct lines. So if I'm looking at the equation x equals 3, then if I want 2 points on that graph, then I need 2 points such that their x value is 3. So maybe I could use 3, 2 and 3, -1. In both these cases, x is equal to 3, so these points are on my line. 3, 2 is right there. 3, -1 is right there, and we get the vertical line through it. For f of x equals -2, that just means our y value has to be -2. So maybe I have 0, -2, and -3, -2. They're saying no matter what x is, the function value is -2, or our y value is -2. I have that in these cases. So we have 0, -2 right there, -3, -2 right there. We connect the dots, and we get our horizontal line. We're going to continue talking about special lines. For now, we're going to look at parallel and perpendicular lines. Parallel lines, hopefully when you think of parallel lines, you think of like railroad tracks kind of deal. They are lines that have the same slope, or in the case of vertical lines, all vertical lines are parallel to each other. We also think of parallel lines as lines that do not intersect, because no matter how long you extend them for, they will never cross. Perpendicular lines, on the other hand, hopefully when you think perpendicular, you're thinking right angles. These are lines whose slopes are opposite reciprocals of each other. So for example, if one slope is a over b, then the opposite reciprocal of that is -b over a. So I think of this as flip the fraction, change the sign. So parallel lines have the same slope. Perpendicular lines have slopes that are opposite reciprocals of each other. So let's take a look at these. We want to find the equation of the line parallel to f of x equals 2 minus 1/2 x that passes through the point 6, -3. So we want to go parallel to this guy. Parallel means they have the same slope. Slope is the coefficient on x. So if we look before our x, our coefficient is -1/2, and the equation of the slope of the line they gave me is a -1/2. I want to go parallel to that, so the slope I want to use is also -1/2 because it's the same slope. So now what I'm doing is I know I want to use a slope of -1/2, and I want to go through the point 6, -3. So let's pretend we're a y equals mx plus b person for a little bit. Then we would substitute in the y value of our point, -3, is equal to our m value, which was a -1/2, times the x value of our point, which was 6. We want to add b, and I need to solve for b. So -3 is equal to -1 times 6 is -3 plus b. If I add 3 to both sides, I get b equals 0. So if I go back to y equals mx plus b, we get y equals, my m value was a -1/2 times x, and then plus b would be plus 0, but I don't really need to write a plus 0. I'll do the perpendicular line as though we are a y minus y1 equals m times x minus x1 person, just so we can see it that way too. So we're working with the same line, but we want to find the equation of the line perpendicular to this line that goes through the point 6, -3. So the slope of the line they gave me was a -1/2. We wrote that here. But if I want the slope of the line perpendicular to that, so I'm just going to say the slope of the perpendicular line, I need to take the slope they gave me, flip the fraction, change the sign. It was -1/2. Now it will be a +2/1, which is 2. So the slope I want to use this time is 2, and I'm going to use the point 6, -3. So I'm going to do this using y minus y1 equals m times x minus x1 this time. You're welcome to use either one of these ways, either y equals mx plus b or y minus y1 equals m times x minus x1, whichever one comes more naturally to you. So I'm going to plug in what I've got. Y minus the y value that I have is -3 is equal to m times x minus the x value is 6. So y minus a -3 simplifies into y plus 3. If I distribute the 2 through the parentheses, I get 2x minus 12. And if I subtract the 3 over, I get y equals 2x minus 15. This line is perpendicular to the original, but it also goes through the point that they asked us to. There's just one more thing we're going to look at in this section, and it is the intersection of lines. So this is going to be a little bit different than some things we've seen in the past. We want to use algebra to find the point at which the lines m of x equals 2x plus 3 and n of x equals -x minus 5 intersect. Well, let's think about what that means. Our m of x has a slope of +2, so it looks something like that. Our graph n of x has a slope of -1, so it's kind of like that-ish. It's close enough. We're looking for this point of intersection. So how are we going to use algebra to do this? Well, at this point of intersection, the x value and the y value is the same in both equations. Because this point is on both lines, when we are sitting at that point, the x value and the y value are the same. Well, the y value of this first function is given by m of x. The y value of the second function is given by n of x. If I want to say that these two functions are equal, so they have the same y value, then I need to take what they're equal to and set them equal. So 2x plus 3 is equal to -x minus 5. So what I'm doing is I'm saying these two functions are equal because I want them to be. I want to find the place where they overlap. If I solve this, I can add the x over. So 3x plus 3 equals a -5. I can subtract the 3 over. 3x equals a -8. Divide by 3, and x is equal to a -8/3. So the place where these two lines meet has an x value of -8/3. Now at this point, it shouldn't matter if I plug into m of x or n of x. I should get the same y value out, but I will make sure of that. So if I plug in -8/3 into my function m, then m of -8/3 is equal to 2 times -8/3 plus 3. And that is -16/3 plus 3, which gives me a -7/3. Let's check to make sure we get the same thing for n of x. N of, I want to evaluate at -8/3, is equal to -8/3 minus 5. The double negatives cancel out, so I'm looking at 8/3 minus 5, and that is indeed equal to a -7/5. So when x is equal to negative 8/3, the y value is negative 7, and I wrote 5. That should be a 3. Negative 7/3. The y value is negative 7/3. This is the point where the two intersect.